Hello everyone, guys. Okay. Hello everyone. So I'm glad to be here to present Filippo Bianchi. He's an associate professor at the Hierarchical University of Norway. He works at the intersection between machine learning, dynamical systems, and complex systems. And today he's going to give us a talk about pooling and also a notebook about this the library that they are developing in their group. And so I'm here to let him the floor and enhance this speak. So
thank you very much. Thanks for the introduction. Okay, so I guess most of you guys are familiar with Genanza and also with some software library for using them. But still, I would try to go as much as possible from the basics and try to build from there. Okay, so to start talking about hierarchical pooling in general, I usually like to make an analogy with traditional deep learning libraries or architecture for computer vision. Here, for example, we have a very famous classic convolutional neural network for image classification, the VGG16. And these kind of models are made by alternating convolutional blocks, which extract the feature from the image, with pooling layers, whose purpose is to reduce and aggregate the information, especially in a sort of gradual fashion. So pooling in CNNs is rather simple to implement. As I say, the purpose is to extract some local summaries from pixels which are adjacent. And here, for example, we can see the most two streamlined ways of doing it, max pooling, which basically takes the maximum value of a pixel in a patch, or average pooling, which, for example, take all the pixels in a patch and then take the average. And as I say, this is quite straightforward because images are regular structures. You can think about them as regularly. So it's very easy to define the concept of a patch and then extract some summaries from those regular patches. Okay, let's now move to graph neural networks. And let's talk about the basic building block of a GNN, which is the message passing layer. So we can build the most standard GNN by stacking more message passing layers. And the role of the message passing layer is to learn some representation for each node. Okay, so let's say that we want to learn representation for the red node here. We apply a function which first processes the feature of the node itself, another function which processes the features of the neighbor, and then a third function which combines them. Okay, and this will give us a new representation of the node, which also account for the features of the neighbors. So the most easy and classic GNN architectures are flat. Okay, they are obtained just by stacking message passing layer. Every time we add a new message passing layer, we are gradually learning representations for the nodes which are more complex, but also which accounts for longer spatial relationship. Okay, so again, if we center here the first message passing layer, for example, look at this neighborhood. The second one will look at nodes which are one step away. Okay, so we are able to consider things which are far apart in the graph. Okay, and those are the flat ones. Those which are more interesting for me and that we will discuss today are the hierarchical ones. So the hierarchical ones alternate message passing with pooling operators, and graph pooling is something which enable to learn smaller version of the graph. Why this is useful? Well, first of all, it allows to expand the accepted field much more quickly compared to just stacking one message passing on top of each other. And that's exactly the same thing that happens in CNN, so in architecture for computer vision. Okay, if we don't have pooling, it will be very difficult to give the model like a more complete global view on the input image. The second is that thanks to this graph pooling, we are able to distill this global information from the graph a bit more gently, okay, and also to direct better, to extract better the things which we are really interested about. Okay, so in what kind of downstream tasks these hierarchical GNN are used? Well, first of all, in graph level tasks, which are, for example, graph classification or graph regression, where we take a graph and we want to assign a label or a value to the whole graph. And here we can just do the same thing that I show you for the VG16. Basically, we alternate message passing and pooling several times until at the end we manage to collapse everything into a single node or a single vector representation that then we present with a readout which gives us the class of the graph. But we can use pooling also for doing node level tasks such as node classification or node regression. Okay, so here we apply pooling, we obtain a smaller graph, we also combine things on this smaller graph, and then we do this operation, which is the unpool or lifting, which takes our small representation and maps it back to the unit space. And then here we can say something about the node themselves, so their class and so on. This architecture is very similar to the unit using computer vision for tasks such as image segmentation. Okay, so we go down, we extract some high-level features, and then we go back in the unit space. Finally, another type that we can use with we can do with graph pooling is detecting community on the graph, and here the output is just the one of the pooling. So there are some pooling operators which I will show you in a second, which basically identify communities or cluster of nodes on the graph, and that per se can just be an interesting result. Okay, if we are, for example, looking for communities in our graph. So a few years ago, we introduced a framework to describe in all the pooling operators, basically. The problem at the time was that every pooling operator was described in a different way, so it was difficult to compare them or to implement them somehow because they were having very different APIs or very different approaches. So what we did here with this framework is to put all the pooling operator under a common umbrella. And actually, I think that the best way of describing pooling is through the SRC framework, which stands for Select, Reduce, and Connect. So basically, a pooling operator can be described as the composition of three functions. The first is the select, which basically identifies the groups of nodes that should be combined or taken into consideration when forming the smaller graph. Okay. So for example, if this is the input graph, the select says that these two nodes should be taken considered together. These two nodes here should be considered together, and then these three nodes should be considered together. Okay, that's this cell operation. It basically spits out some sets of nodes. Then the second operation is the reduce, and the purpose of the reduce is to compute the features of the pool graph. Okay, so it looks at these two nodes. These nodes should be end up together. Okay, so the reduce can say, okay, the features of the pooled graph can be, for example, the sum of the average of these two. Okay, same thing here. We take the average, and here we take the average, and then we have the features of the pooled graph. Next thing to do is to compute the connectivity of the pool graph. And this is done by the connect operator, which defines where edges should be in the pool graph. Okay, and in the end, we end up with this. So different pooling operators, different methods can be obtained, basically all of them, by describing in a different way the select, reduce, and connect operation. I will show you some example in the few slides. But before going to the more complex hierarchy of pooling operator, let's just discuss the most simple one, which is the global pooling. So global pooling, what does, takes all the nodes of a graph and just combines them, okay? In doing this, does not account for topology. So we can think about the select operation to just select all the nodes, okay? Then the reduce operation can be done differently depending if we want to take the average of the nodes, sum them, or take the maximum, okay? And since we end up with a single node, there is no topology there, so the connect operation here doesn't make sense, okay? But now let's go to the more interesting pooling, those which generates a proper graph, not just a node. There are different taxonomies that can be formulated to divide the existing graph pooling operators in different families. The one which I like the most for now is the following. So some class of pooling operators performs a sort of clustering on the nodes, and which means they identify some community. And then the node in the coordinate graph is just given by the combination of the nodes in each cluster. Okay, so this is pretty intuitive. Another family is those which I like to call 1/k, which basically extend the concept of selecting one every other k nodes on the graph. Okay, so for example, we take one, we discard the other, we take one, discard the other, and so on, and we obtain with something like this. Finally, there are the score-based methods, which assign one score to each node, and then the pool graph is the subset, the subgraph of nodes with the highest score. Okay, so those methods basically they chunk away, they cut away a piece of the graph, and that becomes the pool graph. Okay, let's see all these three families in more detail. Let's start with the soft clustering. So at the core of those methods is the formation of those clusters. Okay, basically what we want to do most of the time is to form clusters by aggregating nodes which have similar features and are also strongly connected on the graph. And to describe this partition, we can use a matrix S like this, which basically has as many rows as the number of nodes and as many columns as the community or the super nodes of the graph. Each row here assigns one node to a specific cluster. Okay, this is a hard cluster assignment, meaning that the entries can only be ones or zeros. In general, when we learn things, we don't have a hard situation like this, but we have some soft clustering. I will show you in a second. So this is the general framework for cluster-based pooling operators. First, we have our GNN, and we give an input to the GNN, our topology, represented by an efficiency matrix, and our node features. Then we process this information with a stack of message passing layers, let's say L, and then every time we process this node features and adjacency, our node features become more meaningful. They start to account for information in the neighbors and so on. And what we end up at the end, it's something called x to the power of L, if we apply L message passing layers. And I refer to this as node embeddings. Now, most message passing layer apply a sort of smoothing operation on the features, meaning that every message passing layer takes the node features and makes them more and more similar with those of the neighbors. Of course, there are also some message passing layers which are heterophilic, but now let's focus on those which are homophilic, so they combine things which are connected in the graph. And at the end, what we obtain is something which is similar if it's connected on the graph, which is good. It's a good starting point for computing our soft cluster assignment, because we would like to have things which have similar features and are connected on the graph to end up in the same cluster. So what we can do is to take these node embeddings, put inside something simple like an MLP, and extract the soft cluster assignments from there. Okay, so the soft cluster assignments look like this. Okay, once again, every row represents a node and the columns represent a cluster. So for example, this means that I am assigning vertex 1 to the cluster number 3 with this amount of membership. Okay, note that the sum of the membership, the budget that we have is limited because all the rows have to sum to 1. Okay, so we cannot belong to all the clusters in a maximum way. Okay. Okay, so let's see the workflow now of this kind of pooling operators under the select, reduce, connect perspective. So the first step is that the select takes these node embeddings and compute this cluster assignment. Okay, you can think about really as identifying this sort of assignment, deciding where each node ends up. Okay, so it's really a select. Then the reduce takes these node embeddings and based on the way they are clustered together, computes the feature of the pool graph. Similarly, we take the initial connectivity, the topology of the graph, and depending on how things are connected, we compute the adjacency matrix of the pool graph. At this point, we can apply the new message passing layer on this reduced or this coarse graph. Okay, then we can apply another pooling, another message passing layer, and so on until we reach the end of our GNN architecture. So how do we train these kind of models? Well, first of all, we have the loss for our downstream task. This can be cross entropy if we're doing graph classification, MSE if we're doing graph regression, and so on. So this loss is used to modify the weights, the parameters in the message passing layers and also in the pooling layer. In this case, is the MLP, the weights of the MLP that we are changing, right? However, if we only optimize things using this loss, it's very likely that we end up in a degenerate solution for the cluster assignments. The first one is where all the nodes are assigned to the same cluster. And that's pretty useless, okay, because that would be exactly the same as doing global pooling. The other degenerate solution is that we end up with some uniform membership, meaning that we are assigning every node to all the clusters in the same way, which again is also useless. So to avoid this degenerate solution, we use some auxiliary losses which encourage the formation of well-behaved clusters. So there are many different auxiliary losses and different approaches implement these losses differently. For example, with pool, use a link reconstruction and some entropy. Min cut, use a min cut loss and some orthogonality term and so on. I don't want to go into the details of these methods, but what I want you to think about is that some losses have the purpose, the job of some losses is to ensure that there is some consistency between the topology of the graph and these cluster assignments that we are learning. And the purpose of the other type of loss is to ensure that the clusters are well formed so that those degenerate solutions which I showed you before are avoided. Okay, and depending on how these losses are implementing, the results can be quite different. Okay, so here, for example, it's clustering on citation networks. And we see that if we obtain some losses, we obtain those clusters which are not really separated. Here, the color is the actual class of the nodes. And if we use other losses, we obtain some clusters which are more compact, separated, and are also quite consistent with the actual classes of the nodes. Okay. With other citation network, the results are more or less similar. Okay. So even if the losses try to do more or less the same thing, the way how they do it can make quite some impact. Okay, so we can obtain quite different results choosing one specific type of loss or the other. Okay, so what are the pros and cons of this kind of pooling operators? Well, they are pretty flexible and they retain all the information contained in the original graph, and also this makes them having good performance in the downstream task. However, they have also some downsides. First of all, they have a high complexity, both in space because you have to store this cluster assignment matrix, and also computationally because what we end up having in the end is a tensor. Okay, so after we apply pooling once, we cannot use any more sparse operations. Another thing is that the size of the pool graph is fixed because we have to decide in advance the number of clusters. So we say we want 15 clusters. Okay, good. So every graph in the dataset will end up being pooled in a smaller graph with 15 clusters. So if I have a graph with 100 nodes, we'll end up in a graph with 15. If I have a graph with 10 nodes, we'll also end up in a pool graph with 15. Okay, so datasets where there is a lot of variability in the size of the graph, maybe this cannot be optimal. Okay, let's move to the next family of pooling operator, which are those called 1 over k. So the idea here is to extend the concept of 1 over k sampling from regular structures to graph. So if we think about taking one every other 2 pixels on a regular grid, it's quite intuitive how to do it. If we think about a sequence and we want to say, let's take one element every 4, it's also even more straightforward how to do it. But how to do it on a graph? The concept of one every other node is not really clear because there is not a order between the nodes. So there are a few methods which try to answer this question. And important thing is that these methods, the 1 over k pooling operators, in general, they do not consider the features, but only the topology. Okay, so the first method is Gracklus, and the select operation in Gracklus try to find pairs of nodes which are as connected as possible on the graph. Okay, so for example, these 2 orange nodes, they will end up together. They will be colored in the same way because they are the closest from a topological point of view on the graph. Okay, once after we have done the select, the reduce and connect are quite straightforward. The reduce, basically, we can take the features of the nodes which are colored in the same way and combine them. If we take the max, I hope you agree with me that this it really implements the concept of 1 every other 2 nodes on the graph, right? And the connect here is also quite straightforward. It's basically just coalescing the edges which are incoming to the 2 nodes. Okay, so let's look again at the orange nodes here. So I'm combining these 4 edges entering in this node with these 2. So here we'll have these 4 and these 2. Okay, so I'm just coalescing together these edges. Another method of this family is node decimation pooling, and this is, in my opinion, even better representing the concept of 1 every other 2 nodes. So what this method is trying to do is to find a solution to the max cut partition. So for those of you which are not familiar with the max cut, basically it's a problem that tries to partition the nodes into sets such that there are as many edges as possible going from one set to the other. The max cut problem is also related to the bi-coloring of the graph, which means coloring the node in a way that there are as few nodes as possible connected with the same color. And if you notice, that's basically what's happening here, because you see that this blue one is connected with 2 grays, this blue one is connected with 2 grays. Of course, there are some situations where it's not possible to color 2 nodes differently. You can only do it if the graph is bipartite. But anyway, the MaxCap tries to solve this thing as good as it can. So the select operation in NDP is just trying to do this sort of coloring. Okay. At this point, the reduce here, there is no reduce because what we do is that the blue nodes we keep and the gray one, we throw them away. Why this makes sense? Well, if you think about since we color the nodes in this way, the two partitions that we obtain are as similar as possible, as much redundant as possible. This means that when we do message passing before, nodes which are close by, they will have exchanged a lot of information with each other. So basically it becomes a bit redundant to keep both of them. So we can just keep one and throw away the other, okay? So reduce here, there is no reduce. We just keep the features of the blue node. For the connector, we use here something called cron reduction. I'm not going into the details, but the idea of cron reduction is that we connect two nodes, two blue nodes, if we can reach them in the original graph by walking only on gray nodes. Okay, so for example, to go from this node to this one, I only walk on a gray node. Okay, so good, I put up an edge here. If I want to go from here to here, I have to walk on a blue node, so there will be no edge. Okay, so that's basically the intuition behind the cron connect. Okay, the last method of this family is the chemis, where MI stands for maximal independent set. What is a maximal independent set? Is the maximum number of nodes in the graph such that there are no links between these nodes. Okay, so here, for example, it means that for going to one node of the maximum independent set to the other, I have to do at least 2 hops to reach the next. Okay. Chemis select not only finds the maximum independent set, but also color the remaining nodes, those which are not labeled, assigning them to the closest element in the maximal independent set. Okay. After we have done this, all the nodes are labeled. The reduce simply consists in combining the features of the nodes with the same color, again with the sum, max, average, whatever you want. And the connect, again, is just about coalescing all the edges incoming to the nodes with the same color. Where the K comes from? Well, we can, instead of finding the maximum independent set on the original addition matrix, maybe you don't see from there, but here there is an A. Here I'm considering the maximum independent set on the original matrix. But if I consider the maximum independent set of the K power of the adjacency matrix, well, then it means that I'm finding nodes in this maximum independent set, so that to reach another, I have to do at least 3 hops, okay? And if I consider K equal 3, I need to do 4 hops, okay? So it means that we are selecting nodes which are more and far apart, so less nodes in the graph. And this means that when we are doing this sort of labeling of the unlabeled node, we will end up having much less labels, and then the coarsened graphs will be smaller. Okay. Okay, how do we train these methods, this kind of pooling operator? Well, at this point, we can use only the loss of the downstream task. However, since those pooling, these coarsened graphs do not account for node features, which is basically the only thing that change inside the GNN, we can just pre-compute them at the beginning. This means that we don't need to optimize these layers in any way during training. This also means that training this kind of architecture is as fast as training a flat GNN, actually faster, because every time you apply pooling, the graph becomes smaller, so it needs less operation. Okay, so training GNN with this kind of architecture is extremely fast, faster than standard GNNs. And also the fact that there are no trainable parameters it makes this kind of models good when we have smaller data sets. However, on the downside, since we don't learn pooling, it means also that we have less flexibility, okay? And also, it means that we are not able to account for node features when computing the smaller graph, and also that we cannot find the pool graph which is optimal in terms of some task objective. Okay, the last family of pooling operator are the score-based. So these are quite straightforward. Once again, we have our adjacency matrix, our node features. We process the node features and adjacency with some message passing operators, and then we obtain these node embeddings. Okay. So what this pooling operator do is to apply a projection vector to each of these node embeddings and then extract a single value out of it. Okay. So let's say that our feature here, they have dimension, I don't know, 64. We apply a projection vector of size 64, and we end up with just one value. This value represents the score of that specific node. We can collect all these scores here in a vector that we call S, and then we can apply a top K operation to select the nodes with a higher score. Okay, that's it. So that's pretty straightforward. One thing that we have to keep in mind is that the top K operation is not differentiable. Okay. So how do we do the connect? Well, that's pretty easy. We just look at the nodes which are selected, and then we keep the row and the columns of the adjacency matrix associated with those indices. And the reduce, same thing. We select only the rows of the nodes which are selected. And here, in addition, we also multiply with the score vector. This is done to bypass the non-differentiability of the top K. Okay, so basically, the fact that we are multiplying this with the features that come afterwards means that we are creating a new path where the gradients can flow when we do the optimization. And this is fundamental. Otherwise, our gradient will not be able to reach this projection vector, but not even the parameters of the first message passing layers. Okay. How do we train these models? As before, we need to have a loss that modifies the parameter of the message passing operators. But now this time we have the projection vectors that we have to train. So our loss need to enter also the pooling layers. Okay. So when this kind of method work, so there are different kind of score-based pooling operators, and the main difference between them is the way how they compute these score vectors. Now I just show you the most simple and vanilla one, but other methods, they propose to do something a bit more advanced and elaborate, sophisticated to compute its score vector. However, no matter how you change things, often you end up by having pool graphs, which are just a chunk of the original structure. And when does it work? Well, for example, it works in cases where the cluster graph is given by the presence of a specific substructure. So, for example, if we look at molecular graph, maybe when there is this kind of structure here, it means that this whole molecule is of class 1, and when there is this other structure here, it means that the molecule is of class 2. So in this case, it would be okay to just chunk away a piece of the graph and then use that for classification. Okay, we will just discard a lot of information that in this case would be redundant. So what are the pros and cons of these methods? Very few parameters. Okay, we only have to train the score vector, this projection vector, basically. This also means that they have lower computational complexity compared to the cluster-based methods. However, the downside is that they completely discard some part of the graph formation, which can work in some cases, but it might fail in tasks where it's important to preserve the whole graph structure. Okay. Okay. And this concludes the first part of the lecture, where I gave you like a broad overview of different families of pooling operator. And then the next thing that I want to do today is, which I'm also very excited because it's the first time that I'm doing it, is to present our new library called Core Geometric Pool. And this library is made to be seamlessly integrated with the Python Geometric, which I guess most of you are using already. So what I will do today is to present you, to show you a notebook. This is an introductory notebook, which you can find in the doc of the library. I will give you all the links afterwards. And basically, it shows quickly what are the main functionalities of the library. Okay, so the first thing we can start by checking which are the available pooling operators. At the moment, for me today basically is release day. We have 18 different operators, each one belonging to one of the three families I showed you before. But we plan to add more. Consider that this number is already much higher than the pooling operator which are currently implemented in PyG. Another advantage compared to using PyG is that in PyG, different pooling operators, they have completely different API. So if you want to switch pooling operator in your GNN, it's a pain in the ass. Okay, so instead here it's more simple. You can just basically replace one with another by making basically no modification to your code. Another thing, another advantage compared to PyG is that all those methods we showed you before, which basically are pre-computing the graph, they are done in pre-processing and they are inserted into your data object. Okay, so this makes training much faster compared to PyG implementation, where instead it's recomputing over and over the same thing at every iteration. Okay, the first thing that we do here is to create a top K pooling object. Here we have to specify the number of in channels because, of course, those determine the size of this projection operator and also the K, the pooling ratio. Here, basically, we are saying for each graph, we want to keep 25% of the original nodes. And then we print this pooling operator, and you see that every pooling operator in a TGP has a select, a reduce, a lift, which is the operation to map things back in the original node space, and a connect operation. Okay, they are implemented in different classes, but every pooling operator follows this paradigm. And in addition, we see that we have additional parameters which are specific to each pooling operator. So how do we call a pooling layer? Exactly the same way we're calling a message passing operator in PyG. Okay, so let's start by loading some data and creating a data batch. Here I'm using the classic TUD dataset enzymes, and here I'm creating a batch with the data loader, saying that I want a batch of size 32, and I obtain a data batch object like this with the edges, the node features, and the classes for each graph in the batch. Okay, so if you're using PyG, you're probably familiar with data batches represented in this way. So what we do is that we call the pooler, and then we just pass the node feature, the connectivity, and then batch. The batch object is just an indicator which says where a specific graph ends inside the batch. And then what we get in output is something called pooling output. And it's an object like this, where you immediately recognize some part. For example, here you see that we have the pooling node features, which are much less than the original one, 25% exactly. The pooled edge index, so those are only the connectivity of this smaller graph. And then the new batch, which indicates where each graph ends in the pooled batch. But we have also something new here. The first thing is this SO. What is SO? It stands for select output, which is the output of the select operation. basically it's an object that describes how each node in the original graph are assigned to the nodes in the coarsened graph. Okay, if we print out, we see something like this, which says that this is an object which assigned the original nodes, which are 1092, to the nodes of the coarsened graph, which are 285. Okay, and then each pooling operator implements this differently, but we can think about this object more or less as this matrix S, this cluster assignment matrix, which I showed you before. Okay. So the pooling layer can also be used to perform this lift or unpooling operation, which is mapping the nodes back to the original features. And we see that we only have to do is to call the same object as before. We have to specify here this flag lifting equals true. And this time, of course, we don't pass the original node feature, but we pass the feature of the pool graph. And also we pass the select output because, of course, the lifter needs to know how pooling was done to undo it. Okay, so that's why we are passing the select operation, the select output. And we see here that this is the shape of the original node features and is the same shape also in the lifted node features. Okay, so we effectively mapped back in the original node space. Okay, so there are different types of pooling operator. That is something I showed you before in the slides. And I was having this taxonomy in cluster-based, 1/k, score-based. There are different ways of forming different taxonomies, of course, and the one which is more important from an implementation perspective, if the pooling operator is dense or sparse. Roughly, you can think about cluster-based pooling operator to be dense and the 1/k and the score base to be sparse. So top K that we just saw is sparse. And let's now look instead at a dense pooling operator, Bianchi pooling, which instead belongs to the family of cluster-based operator. So here we have once again to define the number of input features. And this time we have to specify the number of clusters that we want. Okay, so for example, we want 10 clusters. This means that no matter the size of the original graph, it will be mapped in a pool graph with 10 nodes. Okay, we can. This is a very convenient function because we can instantiate a pooling operator only from an alias and from a dictionary of parameters. Okay, and what we obtain is something like this. So here you see that once again, we have a select, reduce, lift, and connect operator. This time, the select and the connector are implemented with the different classes compared to top K. And once again, we have additional parameters specific for the pooler operator. But the syntax is exactly the same, even if these two pooling operators are very different. Okay, so something that sets sparse and dense pooling method apart is the format of the input and output data. Okay, dense method wants a dense input and return a dense tensor in output. Okay, so we don't want to keep track of what is sparse and what is dense, and PGP provides a utility function called preprocessing in each pooling operator, which just puts the data for us in the right format expected by the pooling operator. Okay. Another difference with respect to top K pooling that we saw before is the presence of one or more loss terms in the pooling output. Those are the auxiliary losses which I showed you before, those which are used to avoid the generic solutions. Okay, and we can look at them by checking the values in the loss field inside the pooling output. Okay, so here we see that we have a mean cut loss and an orthogonality loss, which are coming with this layer. And most dense pooling methods have an auxiliary loss, but there are also some a few sparse methods which have also an auxiliary loss. Okay, so that's another rule: who has an auxiliary loss and who doesn't. Okay, so now let's see THP in practice, and let's use it to create a simple GNN with a hierarchy architecture for doing graph classification. The most simple architecture that we can use is one which has a message passing layer, pooling, method passing, global pool, and a linear layer. Okay, so in the init, we specify the message passing layers and the pooling layer, again using its alias and dictionary of parameters, and then the readout. Okay, so the init looks like this. Here we have the first message passing layer. I'm using a simple GCN conv. Here we have pooling. First, we specify the input channels to be the output channel of the GCN conv, so hidden. And then here we specify the pooler from the alias and the dictionary of parameter. And then we have the second message passing layer. So here, the only thing we have to care about is that depending if the pooler is dense or not, we have to use a dense layer or a sparse one. And then we have, again, the readout layer, which is mapping the hidden channels to the output channels, which is the number of classes, for example. Okay. So, as I said, the most important thing here is that the type of pooling operator determines what kind of message layer comes afterwards. If the pooler is sparse, we can keep using sparse message passing layer, such as the standard GCN conv. However, once we use a pooling operator, from that point onwards, we have to use dense layer. Okay, and we can check this looking at this property of the pooling operator. Next, we define the forward pass of the GNN. And here there are a few things to keep in mind that I will discuss in details in a second. The first is this preprocessing step. Afterwards, we just call the pooling layer and we extract the output. Then we call the second message passing layer. We apply global pooling. I will also discuss this in a second. Readout, and then we return something different depending if we have auxiliary losses or not. Okay, so let's look at these three parts with the exclamation mark more in detail. The first is the crossing, which I said must be called before the calling the actual pooling layer in order to put the data in the right format. If the pooler is sparse, preprocessing has no effect. Okay, so it's just like a sort of dummy function that takes something in input and returns exactly the same thing in output. Okay, so we give X edge index, and in output we have exactly the same X and edge index plus this mask object not used here, so it's just none. Things are different if the pooler is dense, because now the node feature will be transformed in a tensor with this shape B and F, where B is the best size. N is the maximum number of nodes in the batch, and F is the size of the node features. Okay, so if we look at the shape, it's 32 because we are using batches of size 32. We have 66 because in this batch we have one graph with 66 nodes, which is the largest one, and then 3 is the number of features, okay? So the other graphs with less than 66 nodes will be padded, okay? And this mask object says basically which nodes are valid and which instead are padded. Similarly, the edge index will be a dense tensor of shape B and N, again, where B is the best size and N is 66, which is the size of the largest graph. The other thing that is worth to pay attention is the global pooling. Global pooling, as we know, has only one job, which is to combine all the current features, all the remaining features in the graph, and is implemented differently if the method is sparse or dense. Why? Well, if sparse, we have to look at this batch object, which indicates to which graph each node belongs to. Why? Well, because if we have 32 graphs, we don't want to combine all the features together, right? We want to combine only the feature of the first graph, the second, and so on. So we have to pass the batch operator. And what we get output is something like this, okay? We have 32 vectors of length 3, okay? Because we combine the feature of all the 32 graphs. In the dense case, our features of the pool graph will be stored in a tensor of this shape, batch k, which we specified before to be 10. So that's the number of supernodes, which again is the same for each graph, and f. So here, pooling is very simple. It can just be done by contracting this dimension with a sum or with an average. And once again, we get in output a vector, a tensor of shape 32, 3. Okay. So no matter if we are using a sparse pooling operator or a dense one, we always end up with a vector of the same size, which is good, right? Because we are completely agnostic to the kind of operator that we are using. We end up with the same thing in the end. Okay, finally, auxiliary losses. Some operators have it, some they don't. So to check if a pooling operator has a loss or not, we can look at this field of the pooling output. If it's not none, we can return the sum of all the auxiliary losses, and those will be passed to the optimizer along with the other losses, like the cross entropy and so on. Okay, let's test our model. So we first create a GNN configured with a sparse pooler, and that's how we do. So here we have the number of features, which in our case are 3, number of classes in enzymes, there are 6. Here we specify the percentage of nodes to keep in this dictionary, and then we create our GNN, okay? Passing these fields, the alias of the pooling operator that we want to use, and then this dictionary of parameters. And then we just call the GNN on our input data, and then we collect the output here, and we see that the output is a tensor of shape 32, 6, because we have 6 classes, and the loss here is just 0. We don't have any auxiliary losses, so we just return a value 0, which does not affect our optimization. Next, we create the same GNN, but this time we only change a couple of things. So the dictionary of parameters, now we're using a dense method, so we have to specify k, the number of supernodes, and then the other thing that we change is the alias. Okay, and that's it. So you see that we have to do really minimal changes for using one pooling operator or the other. Basically, we just have to pass a dictionary of parameters and an alias. And this time we obtain an output, which is again the same as we expect, 32, 6. And the other thing, which is different from before, is that now we have a loss that we have to use and add to our optimizer. Okay. So the final loss is given by then the negative log likelihood loss, which is basically the cross entropy, plus this auxiliary loss of the pooling layer. Okay, and that's it. So we can train this GNN as any other that we normally build with PyG, basically with minimal changes. So before concluding, I want to show you a couple of links. Manage. So first of all, go here. So all the slides which I show you before are taken from a blog which introduce pooling, and this blog is longer, has more content. So please check the blog. I will also give these links to the organizer, which will make it available to you through the log website or Slack maybe. Here we have the link of TG Pool, which I will show you in a second with the documentation and the tutorials. So what I show you now, it's part of the introductory tutorial. There are 2 more, with more advanced features. And finally, this is the website of my group, where we make some posts about our recent activities and news and so on. Okay, this is, by the way, this is the landing page of TGP, and here on the top you have the link to the blog, and here you have the documentation with several things, among which the tutorials, which are 3, and the first one is you can also run it on Colab, and it contains, as I show you, the thing which I showed you before. And that's it.